So the first big theorem in this section is this one, Theorem 1.1. And it's not immediately obvious. It might take a couple read-throughs to really understand what this theorem is saying and how it's useful. It's not immediately obvious. And that's sort of what I'm going to walk through in this video, is to give you an idea of what exactly this theorem is saying, as well as walk through a proof sketch of the theorem. And I'll tell you a bit how we're going to use this theorem in the later theorems, which are certainly more helpful. Okay, so what this theorem is saying, it's telling us something about a graphical sequence, right? So we have the sequence of numbers, non-increasing. D1 is the maximum, dn is the minimum. So non-decreasing sequence, like all graphical sequences should be. And it's telling us something that we can do if we know that a sequence is already graphical. So the idea is we're going to look at this set of graphs, fancy GS. And this is the set of all graphs with S as its degree sequence. So we know, we've seen in the text, there are some examples of two different graphs having the same degree sequence, two non-isomorphic graphs having the same degree sequence. So there might be, in general, many graphs in here. And in particular, we're just going to look at the graphs that are labeled how we want them to be labeled. And it should be clear that up to isomorphism, it doesn't matter how we label our graphs. So it's fair to make this assumption on our graphs that they're labeled in this way, V1 through Vn, where degree of Vi is Di. So that is, the vertex with D1 as its degree will be V1. The vertex with degree 2 will be V2, and so on. And so in particular, we know that the degree of each vertex, say degree of V1, is at least as big as the rest of them. V2, the degree of V2 is at least as big as the rest of the vertices, except for V1. So V3 through Vn, it's at least as big as those, and so on, because this is a non-increasing sequence. Okay. Right, so yeah, that's how all these graphs are going to be labeled. This will be nice for the proof. It'll make it easy. Well, not easy, but like easy in terms of notation, easy to explain. And what this theorem is saying now is in that we can perform this series of two switches to pick a nice graph out of that set of graphs. So what do I mean by nice graph? Now I'll start drawing some things. So we have the set G, GS, and let's take just some graph that might be in there. So given some degree sequence, and let's pick a n, let's pick an order or length of graphical sequence that we're dealing with, as well as a delta. So let's say we're working with order 7 graphs. So our graphical sequence describes some graph of order 7. So we're going to let n equal 7, and let's say delta equals 4. So let's look at a graph that might be an F, and I'll point out how it could be different than this. And I'm going to draw this a certain way. So I'm going to draw V1 here, and as we know, V1 has the highest degree. It has degree delta, right? Degree of V1 is equal to delta, the highest degree. And so it's going to be adjacent to some vertices up here. So I'll draw V2, V3, V4, V5, V6, V7. It has the highest degree. And if it's empty, this theorem is trivial to show. So there's at least some edges going on here. And so V1 with the highest degree is adjacent to some of these. So it's adjacent to exactly delta of these. So maybe it's adjacent to V2 and V3. Maybe it skips over V4. It's adjacent to V5 and V6. Maybe something like this. Here's another example of a graph that might be in GS in this set of graphs, V2, V3, V4, V5, V6, V7. Another graph might look like this, with the same n and the same delta. So maybe it's adjacent to V2, adjacent to V3, adjacent to V4, and adjacent to V5. V2, V3, V4, V5. Notice that 5 here, my delta is 4 in this instance. So my 5 here, this is delta plus 1, so that's helpful in generalizing. It'll always be 1 more than delta, right? Because we start at 2. And then, V6, V7, it's not adjacent to those ones. So maybe it's something like that too. Maybe that's how this first vertex V1 looks. So what we're examining here is the neighborhood, the open neighborhood of V1. Maybe it's something like this. So in this first scenario, right, it's V2, V3, V5, V6. And down here it would be V2, V3, V4, and V5. Maybe it's something like that. Or maybe it's not this at all. Maybe it skips over V2 and it's adjacent to V3, V4, V5, and V7. You know, there's a lot of different possibilities here for this one. But what I'm drawing here is something special. This is a rather nice graph that's in this set, in that V1 is adjacent to just these. This will make it easy to work with these things. Theorem 1.10, this is really just having us manage the notation of the situation, and it's saying that it's okay to do this, that it's okay to assume that if this is a graphical sequence, then we can find a labeling of a graph with that sequence such that the vertex V1 is adjacent to the first delta other vertices like this. And this is just going to make it easy for two more theorems that come after this that'll tell us more about graphical sequences, in particular when they exist. And so this is really the idea here. So how do we prove this? This is the proof that we can always find a graph like this. So yeah, back in the notation, back in the notation of the theorem, this would be, you know, just some arbitrary graph F. This would be like my graph G in the theorem. So every graph H in GS, so I have some graph H. It could look like F, could look like something else. We know it's labeled in this way. It has degree sequence S. What it's saying is we can transform it into the graph G by a series of two switches. And that's the idea. How does this work? Well, the idea is to, if we're in a situation like this one depicted here, the idea is I'm going to find that V4 is adjacent to some other vertex that's not V1 or V5. So it's adjacent to one of these. And I'm going to perform a two switch between that edge that I find and this edge V1, V5. That's going to transfer this edge V1, V5 over to V4. And the idea is I can do this for every edge that's over here that's not in in order. That I can always find this edge. So that's really what we're going to try and prove in this theorem. This is another proof that's by minimum counterexample. So in general, so let's say proof sketch. In general, we want to show that we can do this operation. We can use two switches to find a graph. Find a graph in this set. That is to make neighborhood of V1 into this neighborhood, V2, V3, up to V delta plus 1. Right? In this case, I want to say I can always do this. So one thing to notice here is that if we want the neighborhood of V1 to be this, that this is actually the minimum. If I add up all of the subscripts here, V2, V3, up to V delta plus 1, if I add up all those subscripts, like up here, what will I get? 2 plus 3 plus 4 plus 5. I add up all the subscripts, I get 14. So sum of the subscripts, where Vi is in neighborhood of V1. So if I add up all the subscripts in there, in this case, what did I say I got? I got 14 if I add up all those. And for example, take this one, add up all these. Now I have 2 plus 3, that's 5. That's 16. So here the sum would be 16. So one thing to notice here is that in order to get this neighborhood, we actually, it's sufficient to minimize the degree sum. or sorry, not the degree sum, the subscript sum. That this is at a minimum, the subscript sum is at a minimum when the neighborhood of V1 is exactly this. That's the idea. And so this is how we're going to use minimum counter example. The idea is I can perform a 2-switch. This switching of edges, as I described up here, how we're going to move this edge over here. Yeah, that we can use 2 switches to lessen the degree sum. So what we're going to show is that we can always make this subscript sum smaller. Going to show we can always make the sum of the subscripts smaller. So again, this is for all vi in neighborhood of vi. Yeah, we can always make this smaller. That is, if we just keep doing this process, we'll eventually get down to the minimum, which will correspond to neighborhood of V1 being exactly this set. And so the formal way to do this is with a minimum counter example. So you assume the theorem's false, assume theorem false. Then there must be some minimum counter example. Then there is a counter example such that vi, when you do this sum, such that this sum is at a, sorry, I should have set up here, going to make this sum smaller by a sequence of 2 switches. So if we can't do this, that means that there's some smallest counterexample. So this is at a minimum, but this minimum that we could get with 2 switches is not, in fact, the smallest. So that is, is not equal to V2 through V4 up through V delta plus 1. So the idea is we're going to assume we can't achieve the minimum, the actual minimum. We can't achieve this, and so there's some minimal counterexample that's the smallest. We're going to call this set W from now on and not have to write that every time. Okay, so yeah, like I said, the goal is to talk about a general situation like this, find an edge that I can do a 2-switch with, and make the sum smaller. Okay, so what's our setup? So again, we have a vertex V1, and again, this is just a proof sketch. Hopefully you're reading through with me. So I'll draw a couple of vertices there, V2, V3, that V1 is adjacent to. So maybe it's adjacent to these 2. And then let's say, what do I want to say here? I want to say so if it's not at a minimum, then it has to look, something like this graph up here, something like F, where that is, we skip over some vertex. Now it could be V2, it could be V3. I'm going to draw it in general, some Vj somewhere up here that it skips over. So that is, it's adjacent to all the ones below Vj. So maybe I'll draw Vj minus 1 here. So it's adjacent to all of these ones, and then it skips over Vj. We have to skip something. And then maybe it skips over some other ones. I'll do ... Maybe it skips over some other ones, but then it's adjacent to something else down the line. Right? We know there has to be adjacent to something else down the line. Otherwise, Vj here would have been... Right, we would have used up the full degree. There has to be something else out here. Right, for example, J would be delta plus 2. Right, it has to actually skip over something, be adjacent to something out here. And then there's maybe some other vertices. Maybe it's adjacent to more of those. It doesn't really matter. And then we have Vn here. So this is sort of our general situation. And it's the skipped vertex. So the first skipped vertex, I'm honing in on that one. That's my VJ. So think of VJ as the first skipped vertex. So I'm going to hone in on VJ, and I'm going to hone in on VK, the one that it's adjacent to past it. So the idea is, right, I've labeled, we're just looking at graphs that have this labeling scheme such that, right, degree of VI is greater than or equal to degree of VJ, right? We wrote it in a non-increasing sequence, and DI corresponds to VI, and that's how our graphical sequence is non-decreasing. So that means since we have first skipped vertex and adjacent to some other one, K. So that is, we have J has to be is less than K, and so that is VJ comes before degree. Sorry, I said this bad. Degree of V1, VI greater than or equal to degree of VJ for all J greater than or equal to I. Right, it's bigger than all those. It's not decreasing. So if I have this case, it's Vj, Vk. Since j is less than k, that means that degree of Vj has to be at least as big as degree of Vk, because it comes before it in the sequence, and we've labeled our vertices in this way. So, well, look at this. So Vk is adjacent to V1. So it's already adjacent to something that Vj is not adjacent to. But we know that degree of Vj has to be greater than or equal to Vk. So that means Vj has to be adjacent to some other vertex that's not Vk, because then that would add another degree to Vk, and not V1, because we know Vj is not adjacent to V1. So it has to be adjacent to some other vertex that Vk is not adjacent to. So Vj is adjacent to some vertex, let's say VL, such that Vk, VL is not an edge. Hopefully you can convince yourself of that. If this isn't the case, it's pretty clear. Like, we can do another contradiction proof in here. If this isn't the case, it's clear that degree of Vj will not be greater than or equal to degree of Vk, right? That would make degree of Vk bigger. So this has to be the situation. And so up here in my drawing, I'm going to add this vertex VL. I don't know exactly where this VL occurs. It could occur over here. It could occur over here. I'm just going to draw it. I don't know. I'll draw it here. Let's say this is VL. So that is Vj is adjacent to, did I just draw 6? I believe I meant L. That was weird. Vj is adjacent to VL. And V1 is adjacent to Vk. Right. So now I'm looking at taking this non-edge. We know Vk and VL are not an edge, so taking that non-edge, this edge, and this non-edge, we have a 2-switch. Right? In general, 2-switch looks something like this: non-edge, edge, non-edge, right? And we can do a 2-switch to take this to here without disturbing the degree sequence. So there's my sort of funky looking 4-cycle that goes non-edge, edge, non-edge, edge. And what this is telling me is I can switch the non-edges with edges and not disturb the degree sequence. That is, I can use a 2-switch here. And so we're going to switch that one to over here. Let me, I guess, redraw this. So what does that do? 3VL through Vj minus 1 through Vj, Vk, Vn, V2. VL is maybe over here. So yeah, something like this. This doesn't have to be. Here's Vj, here's Vk, here's Vn. So something like this, as long as I have those in there. So L and J were adjacent. But now I'm doing this 2 switch. So V1, 3, V4, 3L. Up through Vj. Right, so now when I do this 2 switch, this edge, V1, Vk, is getting switched for this edge is getting switched for that edge. So now Vk, Vl are adjacent, Vj, Vl are not. And importantly, V1, Vj is now an edge. And V1, Vk is now not an edge. So after doing that 2 switch, this is what happens. And so, and maybe V1 is still adjacent to something over here, that's fine. All we're trying to show here is that we've made the sum of the subscripts smaller. And that contradicts this minimal counter example. So we made the degree sum smaller. Or I keep saying degree sum, the subscript sum. We made the subscript sum smaller. Contradiction. Right? This was supposed to be the counterexample with smallest subscript sum. But we made it smaller, and so really, again, what this is saying is we can make it smaller and smaller and smaller until we get to this desired neighborhood for V1. So again, it's not clear why exactly we want to do this. We're going to see that in the next theorem, next couple theorems. This is going to branch out sort of in 2 directions here. So now that we have theorem 1.1, sorry, 1.10, theorem 1.10. This is going to branch out. We're going to use this to answer a question. So theorem 1.11. And this is going to answer the question, Right, this answers the question, if 2 graphs have the same degree sequence, if they share the same degree sequence, how are they related? What the theorem says is that they're related by the fact that there's some series or some sequence of 2 switches that you can do to get from one to the other. So any 2 graphs with the same degree sequence are related by a sequence of 2 switches, is what this one is going to say. We're going to use this theorem 1.10 to do that. And we're also going to use this to show the Havel-Hakimi theorem. So this is theorem 1.12, Havel-Hakimi. And so theorem 1.2 is going to answer the question, given a degree sequence, how do we know, or just given a sequence, how do we know if it's graphical or not? And can we produce a graph with that sequence? Is there some way to produce that graph with that sequence? So this is the 2 directions we go from here. I'm going to make videos for both of these, and I'll see you there.